My name is Mark Tinka. I'm MD at Transmission Co. My talk today is going to be about submarine cable systems. So all of you would know that the internet to some degree comes into Malawi via subsea, either on the west coast of Africa or on the east coast of Africa, and then it's transported terrestrially from the coast all the way into Blantyre, Lilongwe, etc. So this talk is really not so much about what a subsea cable is, that we shall do tomorrow. This talk is more about where subsea is going as a scaling approach. And that approach today is called SDM, which is Spatial Division Multiplexing. It's nothing to do with actual spaceships. It's just a term that says we are fitting a lot of stuff into a small space. So just to give you a bit of history, we've had subsea, obviously, since about 1866. Most of it was based on copper. The first fiber optic for subsea transatlantic, this is Europe, North America, was in 56 with TAT1. And ever since that time, subsea represents 99% of all internet traffic, which is close to about 1.5 petabits of traffic today. The initial transmission technologies that we had were obviously based on analog modulation. Now we've moved on to WDM, which is dense wave division multiplexing. So we can have multiple channels. We can have multiple optical channels fitting into a single fiber as opposed to just one. And now the future is how do we improve the capacity of fiber optics? And this is where SDM comes in. And we'll go into what SDM really is all about. There's two key progressions of optical technology over the last, let's say, 50 years. Before that, it was a simple technology known as direct detection, which is essentially just, on-off keying, just creating pulses of light in a sequential fashion. The problem with that, obviously, is that you could only go up to 10 gig because it was very high dispersion. Or in other words, the signal got distorted a lot more quickly. For the last, let's say, 10, 12 years, we've developed a new technology known as coherent. And coherent is essentially based on using not only amplitude for the modulation or for the encoding of data, but rather also adding phase and also as well as adding adding phase as well as polarization. So with that, you're able to encode the data into 3 different sets of information data sets, which is amplitude, phase, and polarity, which actually allows you then to increase your bandwidth. And also, coherent is very different from direct detection in that with coherent, you don't need to worry about dispersion because you can compensate for that in the digital domain, in the mathematical domain at the receiver side. This is some of the coherent evolution technologies. As you can see, 2010 is when it began to come out. About 2011, 2012 is when they began to commercialize it. So we began to see it specifically in subsea, where in subsea, up until that point, every subsea cable was running at 10 gig per wave. Now we have subsea running at 300, 400, 500 gig per wave, thanks to coherent. And as you can see, it started off at 40 nanometer in 2010. We're now up to about 3 nanometer as of today. And in the next 2-3 years, we should be seeing anything from 1.25 nanometer coming out. What does that actually mean? It means that as the DSP gets smaller and smaller and smaller, you're able to pack more and more of them into a board, and which allows you to get the benefits of the technology, but while reducing power, because power is the biggest limitation in subsea, but also in optics in general. And then obviously because of coherent, where you can do a lot of stuff in the digital domain, it gives us the ability to add a lot of other features, like varying stuff like the baud rate, stuff like PCS, which is probabilistic constellation shaping, which allows you to concentrate the power in the lower regions, subcarriers, and so on and so forth. So because of the DSP, which underpins coherent, it's a lot easier for us to add a lot more new features. Also, as part of coherent, but not yet seen on the subsea side, is we're now able to pack all of that technology into a small pluggable. an optic, just like the one you put into your switches, into your routers. And it supports all of those things, 400 gig up to, anywhere from 2 to 400 kilometers. You can tune it just like you would a DWDM box. You can talk to it through the router commands, like you're speaking to it directly. You can program it. And it's also open standard. So MSA, OpenROADM, OpenZR, OIF, these are all open standard, meaning that you can get them from 2 different vendors, and you can get them from any supplier. And you can use them in any device that supports the content management information interface specifications, for example. And also, most importantly, is their low power. So 24 watts, that's a bit low, but in the optical space, it's actually quite high, because if you pack a bunch of these in a router and a switch, they begin to hit up pretty quickly. So it supports encryption as well. And so this is basically how Coherent has helped evolve the space, because a lot of these technologies were only able to find in a big line card from an equipment vendor. Now you can get these in a pluggable. This is the next evolution now, which is 800 gig, also in QSFP-DD format or in OSFP-XD format. Again, highly portable, highly pluggable, easy to scale, 30 watts of power, etc. This is another one that Adva and a few people have been working on. This is for 100 gig. It's different from the previous ones because the previous ones are based on QSFP-DD, which is a double density pluggable. This is a standard QSFP28 pluggable, meaning that if you have a basic router today that has 100 gig connectivity, you can use this. Whereas if you needed to use the other ones, you'd need to have a router that can support QSFP-DD. So it's interesting that 100 gig is getting Coherent last when it came to 400 and 800 gig first. And that's because the demand was not there initially for 100 gig, but it's growing now. So similar to all the Coherent advantages, the difference is this is just 100 gig. Also in the same space, there's the XR. So the Open XR Forum is also doing pluggables that are based on Coherent, but these are point-to multipoint. So for example, like if you do GPON, if you do a GPON access network, or if you do a point-to-multipoint Metro E network, you could use these. For example, this one on the right shows you what it looks like. You can basically have one of those pluggables that is talking to 25 different customers down the fiber at distances that are supported by Coherent. So you're talking tens to hundreds of kilometers, let's say. But then each individual carrier, which is a sub-carrier, like I spoke about before, represents a customer. So if you look just up over here, so these little, you can't see clearly, but those are the sub-carriers. And each of those sub-carriers is about 25 gigs. So you can pack 16 customers in that pluggable, each running at 25 gig. And the next phase of GPON, I think, is going to start going this way, which is how you're going to see 25 gig and 50 gig coming into GPON because of pluggables such as this. They come in both bidirectional as well as 2-core fiber options. This one is primarily being developed by a company called Infinera, recently intended to be acquired by Nokia, but it's an open platform, so you should see these being developed by other vendors also, or if you buy the Infinera one, you will see it also being supported by other vendors as well. So coming back to WDM a little bit, there's 2 formats for how the grid is specified in WDM networks. The first format is a fixed grid, and with fixed grid, what we're essentially saying is that you have a fixed width of bandwidth in the system, typically 50 gigahertz, but nowadays 100 gigahertz, and it's not flexible at all. So if your channel is too wide and starts to edge out on either side of that specific grid space, then you can run into issues. So fixed grids are cheaper systems. They're the most common systems. They're the ones you want to start with when you're building a network. But then as you scale up, you then get the opportunity to move to what we call a flexible grid system. Flex grid systems are exactly what they sound like. They are flexible. They're elastic. You can elongate the spectrum. You can have one service running at 12 gigahertz. You can have another service running at 100 gigahertz. You can have another service running at 150 gigahertz. It all depends on the service you want to maintain for the customer. And this makes it easy because then you're not overusing or underusing spectrum. These are more expensive systems. They are essentially what's shipping now. If you want to buy a brand new system, I would recommend buying a flex grid system because you're going to get a lot more use case and applications out of that. With the flex grid system, as you can see, you can basically have up to 4.8 to 6.1 terahertz of a block of spectrum, and then you can divide it at any width that you like. So anybody know what Shannon's limit is? This should be for the university students, apart from you. No? So they aren't teaching this in university. Not in 2024. Seriously. What are you guys paying for? So essentially, that's the Shannon formula. And let me just see if we can break it down a little bit. So with a subsea cable, once you drop the cable into the sea, that's it. There's nothing more you can do with that. You can't pull it out and upgrade it. It's sunk. It's a sunk upgrade. So that part is B, which is the bandwidth in, like we just spoke about before. That's in megahertz or terahertz or hertz, basically. Then C, the only thing that you can do once you've buried the cable, the only thing then you can improve is the OSNR, which is the optical signal quality, the signal to noise ratio. And you do that by trying to increase C. How many channels can you pump into the system? How wide can they be? That sort of thing. So once you get to this limit, which is Shannon's limit, you need to find other ways to grow the system because there's only a limited amount of SNR or signal quality that's available in the system for you to push a certain amount of capacity or a certain number of channels. Once you get to that point where you're now getting to the peak of Shannon's limit, there's not much more you can do in the optical domain, or even in the digital domain. You now have to look at other mechanisms which tend to be physical, which in the case of this talk is SDM, which allows you to build more fiber pairs into the system. A small overview on what subsea technologies have looked like over the last, let's say, 30, 40 years. Prior to 2010, all subsea cables and pretty much every fiber optic system built was a dispersion managed system. Like I said in the beginning, the problem with direct detection and 10 gig systems was that they suffered from dispersion, which is basically the light spreading out as it travels further. Like if you flash a torch into the night is not straight, it just spreads out. And as the light spreads out, the quality of the signal degrades. That's what we call dispersion. So dispersion managed fiber is you construct special kinds of fibers every couple of 100 kilometers, let's say, that are in either positive or negative dispersion. To compensate for the light spreading. So when the light gets to that point, it will then be compensated for and then corrected for dispersion. But those cables are obviously a lot more difficult to operate because they're more expensive to build. And imagine if you're repairing a dispersion managed fiber, you have to be careful about where you're cutting and what you're adding in to repair, because you need to have the dispersion managed fiber for the sections you need to repair as well. That was prior to 2010. So cables like EIG, cables like EZ, cables like CCOM, cables like WAX, ACE, SAT3, SAFE, all those cables that you know about, those are all pre-2010. Those are all dispersion managed fibers. They were ideally built for 10 gig systems. From 2014 onwards, we now began to build what were known as uncompensated fibers, or highly dispersed fibers. So meaning that in the fiber, you're not compensating for dispersion anymore. Because why? Because coherent. With coherent, you have the digital DSP in the optic, and on the receive side, it mathematically compensates for the dispersion. Because dispersion is what we call a linear phenomenon. We can predict it. We know how and when it will happen. So if you can compensate for it mathematically, it's easy for you to correct it at the end rather than within the system. But most importantly also is that you want to have an uncompensated cable nowadays, because with dispersion, what's happening is the waves are spreading apart. So as the waves spread apart, it's easy for you to carry more of them because there's a bit of spacing. There's a natural amount of spacing as the waves spread apart. So that limits any nonlinear impairments, such as the waves mixing with one another or phasing into one another. So uncompensated cables actually are highly regarded as the way to go in a coherent design. If you don't have a coherent system, then dispersion doesn't make, these cables don't make sense. But in 2024, equipment vendors, fiber manufacturers, optical pluggable manufacturers are all making coherent. They've just about given up on dispersion managed systems. Festoon and unrepeated, what that essentially means is you have a short run, normally under 250 kilometers, let's say. So think of maybe Mombasa to Dar es Salaam, or think of Nakala to Beira, let's say, think of Amanzimtoti to Durban, for example, something like this. So it's normally a coastal route, and it's called a festoon because it festoons in that direction, but because they are so short, they are unrepeated, meaning that they are not amplified. So because they're not amplified, they can be a lot cheaper to run, and apart from getting cut, they'll pretty much last forever. So then SDM is now 2020 and onwards, and SDM is essentially what we're going to be talking about next. So SDM is a mechanism that we use to sidestep the Shannon's limit. And what does that mean? So hold on one second. So in an SDM cable, you have anywhere from 12 to 24 fiber pairs. In a normal cable, it's anywhere from 2 to 8. So the way that works is instead of having pushing the capacity per fiber pair to the extreme, you instead increase the number of fiber pairs. So you can run each fiber pair at a lower capacity, which means you have less nonlinear impact, for example. And because of that, you can pack a lot more of them in a cable. Because also remember, the biggest limiting factor in subsea is power. You can't get power from the sea, so you have to send power from the land on both sides. And because it has to travel, thousands of kilometers, you lose the voltage. So power is a big issue or a big concern with subsea. So with subsea, it's about adding more fiber pairs to the cable, as opposed to mathematically improving the SNR, the signal-to-noise ratio. So if you have more fiber pairs, you don't need to worry so much about the OSNR. And that's the main thing about SDM. It's nothing special. There's no spaceship. There's no funny stuff. It's just adding more fiber pairs into the system. So what does that give you? So obviously, if you have more fiber pairs and you can run each fiber pair at slightly lower power, you really then don't need to have that much amplification. So you can increase the distance between the amplifiers. The typical distance between amplifiers in subsea is about anywhere from 50 to 150 kilometers, let's say. But the more spacing you can have between the amplifiers, the cheaper your system can be to operate, and the less power you need. So SDM is one way to achieve that. Because you have more fiber pairs, you can have longer amplifier spacing, which lowers the power consumption, which improves cost. And then you can also do what is called pump sharing. So basically, a pump is it's a laser. It's basically a laser. It's the pump that pumps the laser into the fiber. In subsea, you normally have one pump per fiber pair, and then you have a backup. But with SDM, you can get to a point where you are sharing the laser pumps with multiple fiber pairs, also to reduce the cost. So there's a cost reduction element also by sharing the pumps. So what does that give you? It gives you a lower launch power, meaning that you don't need to use that much energy to launch the signal into the fiber optic cable. You have a better OSNR because your power is low. Because remember, when you amplify the signal, you also amplify the noise. So if you don't have to amplify the signal too much, you also don't get to amplify the noise. So you get better OSNR, essentially. You also have fewer nonlinear impairments, the main one being polarization mode dispersion, PMD, and the other ones being stuff like cross-wave phasing, four-wave mixing, that sort of thing. Because again, mainly you have low power. When you use low power, you reduce those nonlinear impairments. And also because the specific type of fiber that we use in subsea is of a certain quality, meaning that you can lower the nonlinear impairments also. So an example of an uncompensated fiber system looks like this. The ones from 2015, up to 8 fiber pairs. So you're focusing on maximizing spectral efficiency as well as spectral capacity. You use a lot of power in the amplifier because you have fewer fiber pairs. You can get up to 800 gig per channel today, up to 24 terabits for fiber, and 92 terabits per cable system. That's an uncompensated fiber. For STM, which is a bunch of uncompensated fibers, essentially you can have up to 24 fiber pairs as of today. You're not focusing on spectral efficiency. You're focusing instead on having more fibers. You're not focusing on capacity efficiency because you're running a lower power. So same 800 G per channel, let's say, but you can have up to 576 terabits because you have many, many more fiber pairs. So that's how we are getting around Shannon's limit. And this is just some examples of how the evolution has come across over the last, let's say, couple of decades. Apollo, which was from 03 transatlantic, because of coherent, is now able to do 40 terabits. Then if you look at Anjana, which is a meta cable launching in Q4 this year, 504 terabits SDM based. Okay. So yeah, that's just the benefits that I mentioned before. Lower capacity per fiber pair, meaning that you use less power, which is fantastic. So you have a better OSNR, but you also have room for improvement because you're going in at a lower power. Some of the cables that have been built based on SDM between 2021 and today, plus what's coming again in the future from 2025. Some are in Africa, some are not. Africa, for example, Equiano is an SDM cable. 2Africa is an SDM cable. Peace is not an SDM cable. Simiwi 6, which is being built, is also an SDM cable, if we can get through the Red Sea, let's say, and stuff like that. But there are quite a few challenges also. So if you take a system like this, for example, this is what what do they call open cables? So an open cable is a system where you have the cable that's constructed by one vendor. So let's say NEC, Subcom, ASN, for example, but then you have different operators on the system. So 2Africa is a great example of that, where you've got multiple different people that are using the same fiber or different fibers in the same cable. Equiano is another one, and I think pretty much every new cable coming online will be such a system. And it looks something like this. You've got multiple vendor equipment. You've got a Nokia, you've got a Sienna, you've got an Adva, you've got Infinera, let's say, all plugging into the same ROADM. So how do you manage all of that? So it's a lot more complicated, and this is where stuff like maybe SDA might actually begin to mean something, because it still does nothing to this day. And you know, things like, you know, who is managing spectrum efficiency, who is managing idle channels, who is provisioning, who is testing, all of that sort of thing. So it is rather complex because there's so many fiber pairs involved, and there's only one central person that manages all the others. But this is the future of SDM, and a big part of computational software that supports management of this, because in the old days we just use a spreadsheet in Excel to do capacity planning, but that won't work for this because you're talking about multiple fiber pairs, multiple permutations of point-to-point, multiple drops is the way to go here. To finish off, what's the future? 32 to 40 fiber pairs, let's say, is the next phase. That's going to be a bit challenging because you're thinking about the thickness of the cable, the thickness of the cladding of the fiber itself, and optimizing those things is what could get us there. You also have to think about the limitations of the amplifiers. Can they handle that many fiber pairs? That's a big problem also. There's new ways to fix that. I mean, one of these is an experiment that was done in Japan to sort of see how we can use all of the bands in fiber, so from O, E, S, C, L up to U, to see if we can get more capacity across. With this one, they were able to get almost 400 terabits of capacity across 50 kilometers, so there is hope in that way. But this is expensive because you have different minerals for different bands for amplification. And then obviously there's the new types of fiber that are being developed now. So, one of them is hollow core, so just having no core in the fiber. Others are having multiple cores inside one core, which is multi-core fiber. And then the other one is called few mode fiber, which is just having a couple of modes in one core. So these are some of the ways that we're looking at improving capacity in the fiber. But to be fair, a lot of what will remain standard is A for a long time, which is just a standard single mode fiber, because trying to get this stuff is a bit too sciencey for the moment. All right, that's it. Thank you.
Good morning, everyone. I would like to thank you all for spending your time and effort to participate in these sessions. We believe that these sessions are technical and interactive and started yesterday. And today we are gracing this occasion to launch Malawi-NOG. The conversation about launching Malawi-NOG started probably a couple of years ago in 2022. And as MACRA, we are happy to see the birth of another organization that is going to bring the technical community together to exchange knowledge, experiences, and also network in order to boost the digitization and the quality of our internet services in the country. The number of technical points that I think we are all aware of from yesterday's session. One of the big items that we need to be aware of and participating, especially to the service providers, is about peering. Peering is a critical issue for the quality of internet services in Malawi. We currently have Malawi Internet Exchange, and we believe that the services of Malawi Internet Exchange point can be boosted by, number one, migrating the Internet Exchange from where it is to a more resilient location at the National Data Center managed or hosted by ESCOM. We believe this will provide resilience, and we are looking forward that all operators are able to come hastily to this Malawi Internet Exchange point. The migration has been scheduled to start from the 9th of September, and please put this on your schedules. And on the same 9th of September, the Lilongwe Internet Exchange point will also start installations at the OCL Data Center. The OCL Data Center and the National Data Center are high-quality data centers that will ably manage all the resilience needed to make these internet exchange points serve their purpose and the needs of the operators. Beyond this point, there is conversations that we need as technical people to address. Number one, we need to address security on these networks. We need to address DNSSEC validation on these networks. Currently, as a country, we are not doing very well. We need to address this. Secondly, we have latency issues on our networks. We need to bring in all the tools that are necessary to optimize the quality of these networks. And we also need to improve the caching on these networks, and peering at the exchange points is very, very critical. We also have, in the past 3 months, LionX, an exchange point in Lilongwe. Currently, I think it has 3 peers. I think there is more ISPs with presence in Lilongwe that can easily connect at this exchange point as well. We also need organizations to come to these exchange points, especially the financial services providers, so that we can improve the quality of financial services. We also need to address caching. Currently, caching is being done in silos. TNM has a cache, Airtel have a cache. We believe that if these caches come to the exchange points, they will not only benefit the big guys, but also everybody else will benefit at these exchange points. And we also believe that in your network, if your network is big enough, you should start thinking of creating your own local caches based on traffic that is localized in Zuzu, in Mangochi, in Karonga, in these locations where you see huge traffic. You should be able to set up a local cache for these so that we can localize our traffic and improve the quality of service that currently is very bad. The quality of service, everybody knows in this room, is not where it should be. And we need to start having honest conversations about the quality of service. This starts with the quality of skills in the room. We need to start doing all that we can to improve the quality of skills. We have a lot of students that have come into these sessions from different universities, and MACRA is helping them to attend these sessions and learn. We believe that the operators in this room have the power to bring in more students on attachment basis into their environments so that they can bridge the gap that is there from their academic qualifications to getting them understand what is practically happening in the technical spaces that we come from, and probably they can help us improve the skills that we have in our environments. At this point, I have addressed all the key areas of interest that we believe are important for this session and are important for the quality of service and digitization drive that we are key to in this country. With these few remarks, I would like to say thank you for listening and have a very fruitful training sessions, networking sessions, and friendships should start here. That should help us have very good internet workspaces in Malawi. Thank you very much.